decomposition of the tarballs from the British petroleum oil spill. So in 2010, there was this huge disaster at Deepwater Horizon. A lot of oil was released into the ocean. It was super impactful to the environment, to the economy, and to all of the beaches. This is an image of Orange Beach, Alabama. I hope it shows up well on that screen. But a lot of the oil washed up on these beaches, and they impacted the tourism economy at these beaches. People canceled their reservations, and just disastrous everywhere. So I mentioned the environmental and ecological impacts, but I said the tourism industry earlier. In addition to the tourism industry, one major industry that was affected was the fishing industry, of course. There was $94 million lost in 2010 alone, and it harmed the fish, it harmed the birds, it harmed all sea life and marine mammals around this environment. So now into what we studied. Before I got involved in this, there were professors that went and collected samples from Orange Beach, Alabama, from all of the places where you see the red circles and squares. That's where our samples were collected. And they collected samples over the years of 2010 to 2014. And these were just samples of tarballs that were submerged in the ocean, that were dry, and that came from tarmacs. And so submerged and dry kind of makes sense, but that's a floating tarmac. And those were the types of samples that I analyzed over this time period. And the way we went about analyzing these. First, we had to take the samples, and oil tarballs, when I say tarballs, they're really sticky and really hard, and it's hard to analyze them as is. And so the first thing we had to do was extract them with dichloromethane. And by doing that, we were able to make them more volatile, and we were able to run the tests on them. And from there, we ran the infrared spectra on them, and I'll talk more about that on the next slide, I believe. And then we conducted pyrolysis on them, and we tested them with gas chromatography and mass spectrometry. I know these are some weird words, but I will explain them. Okay, so this is an infrared spectrum. And basically what happens is we extract the sample and we run it through this machine that can show us the bonds that are in these compounds. And it could show us if we have an OH bond on our compound or a double bond to an O. So basically the C's are carbons, the O's are oxygens, and the H's are hydrogens. And as you can see when we ran the infrared on these samples, the top sample is our base sample, and it's what we kept in the lab that was exposed to no weathering over the years. It has no little dip at where the OH bond is pointing. Okay, but as you go down, you get more weathered samples over the years. I think the bottom one is the 2014 one, and the second one is actually just a few months after the oil spill. And what we can tell by that little dip at the OH peak is that there was some oxidation that took place in the environment while these tarballs were exposed to the aquatic environment that they were in. Okay, well then we ran the gas chromatography on these samples. And what gas chromatography, mass spectrometry is we put these samples in a machine and it pushes them through with helium. And as they go through, you know, heavier samples are going to take longer to go through. I mean, that just makes sense, right? So it's a very small tube, and these samples with a lot of carbons are going to come through at a later time than the samples with less carbons. And so what we're able to do is we're able to analyze the amount of the less carbons, which are over here. That starts at 10 carbon chains, and it goes all the way to there's a 30 carbon chain. And by carbon chains, I mean something that looks like that. It's got the black balls are carbons and all of the white balls are hydrogens. And so this is what we call a hydrocarbon. So you'll hear me say that more in the later slides of this presentation. But anyway, so what we can tell from this is that over the years, on this one, our base sample that was kept in the lab is on the bottom, and the more weathered samples are going up. What we can tell over the years is that after 2 months, most of those smaller carbons are gone. And then after a year about, most of the larger carbons are gone, and we're just left with this residue material that causes that lump at the end. And so you can look at this and you can't really analyze that later data, right, the 2014 year. There's not a lot of stuff that you can look at and you can say, okay, well, how can I test this and show how the environment has affected these tar balls? There's nothing I can do there. So we had to find a different way. So we did extraction and then did pyrolysis. And like I said, extraction was dichloromethane. And that's really a substance that makes it more volatile and makes it less sticky. And pyrolysis, that's thermal decomposition of it. What we did is we took the sample and we put it in a vacuum sealed tube and then put that tube in a furnace and ran it at a certain temperature for a certain time, and the sample decomposed into hydrocarbons that we were more able to analyze. And you will see the graphs that, compared to the last one, there's a lot more information there for you to analyze. Okay, the first step of the pyrolysis was to figure out what temperature we wanted to do it at. So we tried different temperatures on the same sample. And the bottom temperature is 410 degrees. And as you can tell, there's a lot of the longer chain carbons there for us to analyze, but there's not a lot of the shorter chain carbons. So that wasn't really a very valid way to analyze the relationship between these. But when we ran it at 500 degrees, there's nothing. So we couldn't analyze it there either. So what we decided to go with was the second peak, the blue one, and that was 440 degrees Celsius, because that gave us the most information for us to do our analysis with. And what we did is we ran each sample at 440 degrees Celsius in this furnace for 30 minutes each. So these are some pictures of me putting a sample in, because we did several of these samples, but this is just one. And what we did, or what I did for each of these, was weigh out a certain amount of the sample on a piece of aluminum foil and then slide it into one of these Pyrex tubes. And then we would connect it to a machine that would create a vacuum in the tube. And I would put it up to a torch, I forgot the word there. I put it up to a torch and seal the tube off, and that's where you get the little tip on the end of the tube, and then I put it in a metal tubing, which we would then insert into a furnace at 440 degrees Celsius for 30 minutes, and it would come out looking like that. And so what we would do with that is we would break that open with a hammer and then extract what was in that tubing to do the testing on. Okay, so this is pyrolysis not of our compounds, but of simple long-chain carbon compounds. And I told you what a carbon compound chain looks like. It's like the little chain. It's all just carbons connected to hydrogens. And so these, the bottom one, has 20 carbons and 24 carbons, and it goes up from there on those three. And what you can see here is that the saturated peaks, which I will tell you what saturated and unsaturated is in a second, but the saturated peak is much smaller than the unsaturated peak. So what is a saturated and unsaturated hydrocarbon? All right? This is a saturated hydrocarbon. Every little black dot has fully connected to your hydrogens, all right? I'm going to lay that there. But what we see as an unsaturated hydrocarbon is a hydrocarbon that has a double bond or something like that between two carbons. So what you have on the end is you're going to have one less hydrogen and then one less hydrogen there. So we can measure it by seeing the differences in mass, because it's going to go down one or two since they're lacking in hydrogens. And that double bond on that unsaturated hydrocarbon, it can be on the end, or it can be on the second one, or it can be on the third one, and so on. So you can have several different possibilities of it. Okay, so this is our gas chromatography of our samples. And I know that's a little difficult to read. I will zoom in to this graph after I speak about this for a little bit. But what you can tell here is you don't see that difference in the peak from the unsaturated and the saturated. And they're more equal, but over time, the saturated and the unsaturated change in equality, and you get more saturated than unsaturated. Okay, and you can see that better on that graph. It's closer up. That's from a 10-chain carbon to a 14-chain carbon. And the top sample is more weathered than the bottom sample. The very bottom sample is our sample that we kept in lab. And so that's a little bit of a difference. So, we could analyze that. We could see, okay, is this how we could test for how the environment is impacting these carbons over time? Okay, so this is just a close-up of the graph that I just showed you, but it's only including the 2010 sample and the 2014 sample. And it better shows you how the difference in the unsaturated and saturated peaks are, because I know it's a little difficult on the last graph when you have more of them. But there is a difference there, and so we went from that to analyze it by doing the ratio of the saturated to the unsaturated hydrocarbons. And these ratios, our ratios are on the left from here on, and then these ratios are those of the simple long-chain hydrocarbons that we talked about before we went into our samples. And as you can tell, there is a great difference there. The long-chain hydrocarbons have much more unsaturated than saturated hydrocarbons. And that kind of shows us how they're not the same. Those are completely different, first off. And then second off, when you analyze this data, you can see that the ratio of saturated to unsaturated in our samples alone, it increases in the more weathered samples. Because from here, we have a smaller line than over here. Now on this graph, I know it's labeled, but the carbon 14 chains to the carbon 18 chains are in red, and the carbon 10 chains to the carbon 13 chains are in blue. And you can obviously tell a difference in the longer chain carbons than in the shorter chain carbons. There's a much greater ratio of saturated to unsaturated in the longer chain carbons than in the shorter chain carbons. So what all data did we just talk about? I know that's a lot of information. Basically, what we can tell from our peaks is that we have straight chain saturated hydrocarbons after the pyrolysis, but we have both branched and straight chain unsaturated hydrocarbons, because as you can tell from the ratio, there's a little difference there. Okay, and these are our ratios that we just talked about. I didn't say the numbers, I just pointed out the sizes and how they look different, but the saturated to unsaturated hydrocarbons in the simple compounds, which were on the right in that last slide we looked over, they had about a 1:5 ratio. And the ratio of the carbon 10 to the carbon 13s, which were the smaller lines, there was about a 1:1 ratio, but over time it became more of a 2:1 ratio. No, the carbon 14 to carbon 18 was a 2:1 ratio. And over time, the carbon 14 to carbon 18 ratio increased from 2.5 to 1 to 4 to 1. It kind of increased over time. So what do we find from this? All right, so pyrolysis, I talked about the one with the furnace where I heated the samples and we were more able to analyze this data. It showed that pyrolysis was a more valid way to analyze these hydrocarbons as they decompose in an aquatic environment over time. Now, we looked at the IR, there were small OH peaks, which shows us that there was some oxidation. However, that's not enough information for us to analyze the impact of the environment over time on these hydrocarbons. There just wasn't enough information there. And so what we can take from that is that there is definitely still more research to be done and more set environments in the lab to draw a specific conclusion as to the relationship between the weathering of compounds over time and their data that we drew today. There's definitely a relationship, as we were able to draw, but there is more research to be done there. All right. And I would like to finally thank Dr. Greco and the Department of Chemistry and Geosciences for allowing me to conduct this research over time, and also thank the people who were able to collect these tarball samples for me to analyze and do this research. Any questions?